Welcome to my YouTube channel. In this video lecture, I'm going to answer question 11 to question 20 of DME chapter in Kit Williams Radio Lab. So let's begin. Question 11. Simple. The DME operates within the frequency band of 962 megahertz से लेके 1213 megahertz. So average 1000 megahertz. And this frequency band is UHF, ultra high frequency band. Okay, so the correct answer here will be option delta, 962 to 1213 megahertz. Important. Next, a DME is located at mean sea level. Aircraft is passing vertically above the station at flight level 360. It will obtain a DME range of approximately how much? So very important. Let's say this is your DME station on the ground. There is aircraft here. Now when this aircraft is this much away from the DME station, it will get to see its land range in the cockpit. So this land range will be this much, like this. Okay, this will be the slant range. Now when this aircraft continues flying towards the DME station, DME ground station, this land range will progressively become angled upwards, meaning now this land range will be angled like this. Right? So first it was like this, then it will become like this, then like this, then like this. So as aircraft approaches the DME station, the slant range will start becoming angled vertically upwards. Okay, so there will come up when it will be very far away from the DME station. I hope you understand this. The slant range will be very flat. Okay, just like the horizontal range, horizontal ground distance, just like the horizontal ground distance. As it approaches the DME station, this slant range will start becoming vertically inclined upwards. Okay, so as it closes on the DME station, the slant range will angle upwards, then like this, and then finally when it is directly above the DME station, the slant range will be perpendicular, that is 90° up, 90° line 90° above the DME station. So here in this case, the slant range will equal to vertical distance of aircraft above the DME station. Remember this, okay? Vertically above the DME station. This is your DME station, so vertically above it. This is very important to understand. So now in this case, it's given to you that aircraft is vertically above the DME station, vertically above the DME station at flight level 360. Okay, flight level 360. So this will be indicated on your DME equipment as a slant range. Okay, as a slant range equal to 6 nautical miles. Okay, slant range will still be shown, but you must be aware of the fact that whenever you are above the DME station, this slant range is nothing but equal to your, okay, it is nothing but equal to your vertical distance above the DME station. Okay, vertical distance above the DME station. So in this case, slant range will be 6 nautical miles, meaning you are 36,000 feet above the DME station. Question 13. During a flight at flight level 210, that is 21,000 feet, a pilot doesn't receive any DME distance indication from a DME station. located approximately 220 nautical miles away. What is the reason? Now all DME transmissions obey line of sight rule, meaning aircraft must be within the range and in the in the height boundary inside the height boundary to successfully receive DME transmissions, ground transmissions. Okay. So line of sight formula is 1.25 or 1.23, different books, different figures. Height of aircraft plus square root of height of the ground station. Now in this question, the height of aircraft is flight level 210. Okay. So 1.25 square root of 21,000 feet. Ground station is at on the ground, so 0. So 1.25 multiplied by square root of 21,000 is 144.9 or 145. So into 1.25 is 181. So 181 nautical miles. This means that aircraft will be able to receive DME transmissions only if it is 181 nautical miles or less from the DME station. From the DME station. Remember. But in this case, we have been told that aircraft is 220 nautical miles away. That means it is more than 180 nautical miles away from the DME station. It is out of the range. Okay, so that's why it doesn't receive any DME distance information because it is out of the line of sight range. So correct answer here is aeroplane is below the line of sight altitude. Aeroplane is circling around the station. Altitude is too high. Range is always less than 200 nautical miles. Now the next important point is aircraft is at flight level 210. Okay, aircraft is at flight level 210. So it should be the distance should be 181 nautical miles and aircraft is at 220 nautical miles away. 181. So aircraft is too high. Flight level 210 is too high a vertical distance or altitude for 220 nautical miles. So the correct answer here will be option Charlie. Next. Okay. A typical frequency employed in distance measuring equipment is 1000 megahertz. The frequency band begins from 960 to 1213 megahertz. So average is 1000 megahertz. So the correct option is option Bravo. Next, 15. Distance measuring equipment operates in the UHF band and is a secondary radar system. Very important question. We all know that distance measuring equipment operates in the frequency band of 960 MHz to 1213 MHz, and this frequency band is the UHF ultra high frequency band. Next thing, DME is based on the operation of secondary radar principle. What is the difference between a secondary radar and a primary radar? In case of primary radar, let's say this is your aircraft target. Do watch my radar lectures also, you will get better understanding. I will explain this in short. This is your aircraft in the atmosphere. Here is your DME, or let's say primary radar on the ground. This primary radar will transmit radio pulses in the direction of this aircraft target. This radio pulses will strike the aircraft and get reflected back at the primary radar situated on the ground. In this case, in case of primary radar, the transmitter and receiver are going to be the same ground station. The frequency at which these waves are transmitted is the same frequency at which they will get reflected from your aircraft target. But in case of secondary radar, the opposite happens. Here is your secondary radar situated on the ground. There is aircraft in the atmosphere. This secondary surveillance radar on the ground will transmit radio pulses in the direction of aircraft at a particular frequency called 1030 megahertz. Aircraft will respond to this interrogation pulses by sending a reply pulse in the direction of the secondary radar situated on the ground. The frequency at which this aircraft replies is going to be 1090 megahertz. So as you can see, the transmitted frequency is different from reception frequency. In case of primary radar, both the frequencies of transmission and reception were the same, but here in secondary radar they are different. So this is the essence or significance of secondary radar. The transmitted frequency is different from reception frequency. And DME operates on secondary radar principle. How? In case of DME, your aircraft is your interrogator and the ground station becomes your transponder. Next, aircraft DME equipment will transmit interrogation in the direction in all directions. Okay, it will transmit interrogation pulses in all directions or omnidirectional. Ground transponder will receive this interrogation pulse, wait for 50 microseconds, very important point here, wait for 50 microseconds and reply by retransmitting pulses omnidirectionally in all directions, omnidirection. A very important point. The reply frequency or the frequency at which the pulses are replied, the reply frequency will be 63 megahertz. Remember this value, 63 megahertz different from from the from transmitted frequency. from transmitted frequency. Okay, so this is the principle of operation. 63 megahertz means if the interrogation frequency is, let's say, 100 megahertz, it is not 100 but for example 100 megahertz, so the reception frequency will be 63 megahertz different from 100, meaning it can be either 100 plus 63 163 or 100 minus 63 37. So that is the meaning. So correct answer is delta, UHF band and a secondary radar system. For a conventionally for a conventional DME facility, very important, beacon saturation will occur. Beacon saturation will occur when the number of simultaneous interrogation exceeds what value? Very important. Remember, theoretically, 126 aircraft can use a DME station. Can use a DME station at one time. Very important. The scan rate if the scan rate is not very high. Point number two, but we know that there will be many aircraft that want to lock on to the DME station. Locking on to the DME station means using that DME station. There will be many aircraft that will want to lock on to the DME station and use it. So you're finally practically 100 aircraft can use a DME station at one time. At one time. Okay. Next very important point is that you have to remember beacon saturation. The meaning of beacon saturation. So what is beacon saturation? It is nothing but beacon saturation is the name given the apparent error is the name given to the apparent error caused by stronger signals preventing aircraft stronger signals preventing aircraft receiving a range receiving a range, meaning airborne equipment transmitting transmitting at higher power will push out some older, closer airborne equipment which has a lower transmitter which has a lower transmitter power. Okay, which has a lower transmitter power. So the correct answer will be for a conventional DME. Practically only 100 aircraft can use it at one time, because we assume that many aircraft, or consider that many aircraft in the airspace will want to use the facility of the DME station. So only 100 best aircraft, okay, which are able to lock onto the DME station will will achieve that DME service or DME distance information. Theoretically, it is 126 aircraft. Next, question number 17. On a DME, display counters rotating throughout the range indicates. Now, whenever your aircraft has achieved a lock on, whenever aircraft achieves a lock on, it gets a DME information or DME indication. But whenever aircraft loses the lock on, okay, it loses the lock on, the DME airborne equipment will begin a range search. A range search is nothing but looking for, in simple words, looking for DME transponder on the ground to achieve a lock on. Okay, again it will start searching for a proper DME station to achieve a lock on. Okay, so this is the meaning of display counters rotating. So it indicates airborne failure, no. It indicates airborne receiver is conducting a range search, yes. Ground equipment failure, no. Airborne equipment is conducting a frequency search, no. So option Bravo. Next. 18. The aircraft DME receiver is able to accept replies to its own transmissions and reject pulses replied to other aircraft. How? So there are two things. Remember, now your aircraft first is able to accept its own replies and not ground reflections. This is one question. In the previous lecture, in the first 10 questions I solved, there was one question which asked, how does aircraft DME receiver is able to accept replies to its own transmissions and rejects replies coming from any ground reflections or echoes coming from any other object. Now here they are talking about how does it reject replies intended for other aircraft. Okay, so I will give the comparison between both concepts. So one is able to accept its own replies and not ground reflections. The second is able to accept its own replies and not the replies which are intended or meant for other aircraft. So situation 1. Now this is achieved because DME works on the basis of secondary radar. I have explained just now how the secondary radar operates. So DME works on the principle of secondary radar. So the transmission frequency and reception frequency will be different will be different by 63 megahertz by 63 megahertz. Okay, so this is how it is able to accept its replies, only its own replies, and eliminates replies coming from ground reflections or other things. Now in this case, how does it accept its own replies? How does it know that the reply that is coming at its door belongs to it and not to any other aircraft? So the replies are jittered, meaning the interval among the replies among the radar pulses, the time interval among the radar pulses is different for each and every aircraft. Okay, so let's say for example, in case of aircraft number one, this is your aircraft one. In this case, the time interval between two consecutive pulses is, let's say, for simplicity of understanding, 5 seconds. Okay, so this will be maintained throughout the cycle for this particular aircraft. There is another aircraft in the atmosphere which is using the same DME station. The reply pulses for this particular aircraft number 2. Okay, the reply pulses for this particular aircraft number 2. The time interval between the reply pulses of this particular aircraft will be, let's say, 7 seconds. Is 7 seconds. Okay, so this is how the reply pulses are unique to every aircraft. So the aircraft number one will accept those replies only which have a time interval of 5 seconds between them. Aircraft 2 will accept those replies or that replies only which have a time interval of 7 seconds. This is called jittering. So the correct answer here is, so remember, for concept 1 or situation 1, this is the answer. Okay, and situation number 2, this is the answer. So the questions can be framed both ways. Now question 18 option A, pulse pairs are amplitude modulated. No. Pulse pairs are discrete. Discrete means unique, special to particular aircraft. Aircraft interrogation signals and transponder responses are 63 megahertz removed from each other. This is right. They are removed from 63 megahertz different, but this answer or this option is relevant to this situation. We are currently concerned about situation number 2. So option C is also wrong. Transmission frequencies are 63 megahertz different for each aircraft? No, not for each aircraft. It is between aircraft and the ground station. So delta is wrong. Correct option is option Bravo. Pulse pairs are discrete to a particular aircraft like this, like I explained. Next, question 19. Aircraft DME receiver can't lock on to interrogation signals reflected from the ground. Now here we are going to apply this reason. Okay, situation number 1. So why aircraft transmitter and DME ground are transmitting on different frequencies? Yes, like I said here, secondary radar principle, transmission and reception frequencies different by 63 megahertz. Bravo, wrong. Reflections are subject to Doppler shift. DME transmits twin pulses. DME pulse recurrence rates are varied. This is for this option delta belongs to situation number 2 between two different aircraft. For situation number 1, option A is the correct. Question 20. The design requirements for DME stipulate that at a range of 100 miles, the maximum error should not exceed how much? So according to ICAO, accuracy is plus minus 0.25 nautical miles plus plus minus plus 1.25% of the range. So over here the range given to us is 100 nautical miles. So 1.25% of the range, that is 1.25% of the range, that is 100, is 1.25. Now you are going to add this 1.25 to plus or minus 0.25 nautical miles. So the answer will be 0.25 plus 0.25 is 1.5 nautical miles, and 1.25 minus 0.25 is 1 nautical mile. So if the range is 100 nautical miles, the DME information or indication should be accurate, or should be accurate within 1 nautical mile or 1.5 nautical mile. So here they have asked that it should not exceed. So they are talking about exceeding a particular limit, means being more than something. So in that case, we will mark this answer 1.5, which is 1.25 plus 0.25. Okay, so the correct answer will be option alpha, 1.5 nautical miles. So this concludes our lecture. I hope you have understood all the 10 questions, the explanations I gave, the answers. If you have any doubt, any comment, feedback, let me know in the comment box of this video lecture. I request you all to subscribe to this channel if you have not yet, and share this video with your friends. If you have liked this video lecture, you can let me know that by clicking the like button on the YouTube on this YouTube video, and also don't miss my next video lecture in which I will be answering the next 10 questions of this chapter. So I'll see you there. Thank you for your time.